our second short answer question from Unit 3. The small block of mass 150 grams is placed at a point A, a height 2 meters above the bottom of a track, as shown in the figure. It's released from rest. It slides with negligible friction down the track around the inside of the loop of radius 0.6 meters and leaves the track at point C at a height of 0.50 meters above the bottom of the track. So part A is a pretty straightforward conservation of energy question. So you calculate the speed of the block when it leaves the track at point C. There's no friction anywhere on the track, so honestly, between point A and point C, it doesn't make any difference that it goes through the loop there. We just have to do total energy before is equal to total energy after. And so we get mgh plus 1/2 mv squared at the top equals mgh plus 1/2 mv squared at the bottom. Our mass is equal to this everywhere. Our original height is equal to 2 meters. The original speed is equal to 0. When it launches, the height is equal to 0.5 meters, and the v is what we're searching for. So a little bit of algebra gets us a velocity of, 5.4 meters per second. 1 point for a correct conservation of energy equation, 1 point for the correct answer. Part B wants you to draw and label the forces, not components, that act on the block when it's at the top of the loop at point B. So there's two things there. We've got gravity acting down. We've also got a normal force acting down. So two arrows coming out of the same block there. So we get 1 point for drawing and labeling the weight. We get 1 point for drawing and labeling the normal force, and 1 point for no extra forces. So 3 points for part B. For part C, we're going to do something that we've done before. We're going to find the minimum speed that the cart needs, or the block needs, at point B in order to maintain contact with the track. So we remember that for that case, the normal force is going to be equal to 0. And we have the net force is just going to be equal to mg, because back here at our little free body diagram, there's not going to be a normal force. The net force is due to gravity, and that's going to give us, it's going to act as a centripetal force. So again, knowing the radius of the curve is really all you need to find the velocity is 2.4 meters per second. So 1 for a correct equation that can be solved for speed, somehow equating the weight of that block to mv squared over r. 1 point for the correct answer, and that's part C. Finally, we know that in the original setup, the ramp is 2 meters high on the left. But this question is, what's the minimum height that we need at the beginning to make it through the loop? So if you're designing a roller coaster, how high does that first hill have to be? So we have another mgh equals 1/2 mv squared plus mgh. So here's my beginning of the problem. Here is my top of the loop. That gives us an initial height of 1/2 mv squared plus mgh over mg. Now, over here on the right-hand side, we know the mass, but we learned from step C that the minimum velocity here is 2.4 meters per second. We learned that there. It's not 0. It's got to have some speed to go through there. So we had to substitute that speed that we got from the last problem. And we know that the height is 1.2 meters, because if you look at the picture, the radius is 60 centimeters, and we've got to be 2 radiuses up there. So solving for the height, we get 1.5 meters, and that, just double checking, the original height was 2.0 meters, so we're in the right ballpark there. So 1 point for conservation of energy, 1 point for correct substitution of the velocity from part C, and 1 point for the correct answer. And that's it. That's your second short answer question from Unit 3.